Not every carbon is chiral. That was projecting a second ago, wasn't it? When did it decide to stop doing that? And why did it stop doing that? Pardon me, we're having technical difficulties. Okay, whenever you kind of lose the slide, let me know, because I'm looking at this and thinking. There we go. All right. So this carbon down here, let me see your molecule. This carbon down here, the bottom carbon, which is this one right here. And notice what we're doing. The top is carbon number 1. There's your aldehyde functional group. That is the distinguishing group on this molecule. Yes, we got hydroxyls on every carbon except the top one, which has a carbonyl. That's carbon 1, 2, 3, 4, 5, 6. And what you will see pretty generally here is we will draw these vertically. We'll draw them vertically. We're going to look at them vertically. We're going to get used to examining them vertically with the carbonyl at the top. This is an aldose. So the carbonyl is on the end, and that end is carbon 1. Fructose, the carbonyl is going to be right here, and then we're still going to move that up towards the top. That's going to be carbon number 2 for fructose. It'll be 1, 2, 3, 4, 5, 6. But this is glucose. Carbon 1, 2, 3, 4, 5, 6. So let's look at carbon 6 right here. Is that a chiral carbon? No. Because you have 2 things that are the same, and you only can have 4 things on a carbon, they cannot have 4 different things on it, right? Because it's got 2 things that are the same. So whenever you see 2 hydrogens or 2 of anything that are identical, then it's not a chiral carbon. But this carbon is. This carbon. It has 1, 2, 3, 4 different things on it. You know, if you say what is above here. So there's a carbon here. What you're looking at right here is a Fischer projection of the glucose molecule. I'm not even drawing the carbon. All right? Whether you draw the carbon there or not, it's a Fischer projection. All right. So what I'm going to do here, this is glucose. This is glyceraldehyde. This is glyceraldehyde. It's 3 carbons long. But it has a CH2OH at the bottom. The next carbon up has an OH and an H. And then it has the aldehyde at the top because it's only 3 carbons big. But glyceraldehyde, so the right and left hands are mirror images of each other. Let's just get over to glyceraldehyde. Fischer projections. So we're going to start talking about Fischer projections. This is where the D and the L come in. What do we mean by D and L? I kind of wish this was over here and this was over here. Because L is, you're going to see in a minute, it doesn't stand for left, but you could use that to help you remember. So let's see what we got here. A Fischer projection. Now this is what I'm going to want you to do with your glucose. Now, I'll give you this back in a second, but I'm going to want you to concentrate on these bottom 3 carbons. Even though glucose is not exactly the same as this, it goes on up. It's got 3 more carbons. But we're going to want to compare these bottom 3 carbons of the glucose, your glucose, with the 3 carbons of the glyceraldehyde. This is our standard. This is our reference molecule for deciding what is D and what is L. We're going to find this, that we even come back to this molecule to decide whether an amino acid is D or L. We're going to come back to this 3-carbon monosaccharide. You follow me? This is our reference. So what do? On a Fisher projection, you orient the carbons vertically. You have the carbons fade away from you. So if you think of your chirocarbon being right on the board, think of the other 2 carbons being behind the board. And so what does that mean? That means that the OH on this chirocarbon, this is the only chirocarbon on glyceraldehyde. This is not chiral. It's got 2 hydrogens, an OH, and that. Because it has 2 things that are the same, it's not a chirocarbon. Is that a chirocarbon? No, it only has 3 things on it. 1, 2, 3. So this is not a chirocarbon. So the only chirocarbon for glyceraldehyde is the middle carbon. Yep. Everybody with me? I'm trying to go one step at a time, but stick with me. All right? That's the only chirocarbon. So, for a Fisher projection, what you do is you orient the carbons vertically. The carbons are behind you, facing you. So if I was looking at this to see if this is D or L, I would look at it. I would face it. And the OH and the hydrogen are projecting towards you. If the OH is on the right, it is D. And if the OH is on the left, you see these 2? These are 2 glyceraldehydes. But they're different. See where they're different? Look at this OH right here. That OH is on the right. That's D glyceraldehyde. This OH right here is on the left, and that's L glyceraldehyde. If it is on the left, it's an L. If it is on the left, it is not a naturally occurring glyceraldehyde. This is what nature makes. D glyceraldehyde. You follow me? All right, take a look at them. D, L. Now what am I doing? I have the 3 carbons up and down, straight up and down, and they're back, away from you. I'm projecting the OH and the H towards you. Am I moving around too much for you to see? I've been FaceTiming with my grandson, Toph, and he's just, the phone's always moving, and I get dizzy. Toph, set the phone up on the counter. Dude, quit moving the phone. You go out, I gotta go out. It's just crazy. So I said, just prop it up and let's talk. And so that works better.
And that OH that you're looking at is the one in the chiral one, right?
One on the chiral carbon. All right. So now what I want you to do is, let's take yours again. What you need to do is you need to kind of stretch this thing out. You need to get your carbonyl at the top, and I want you to examine. Don't try to get all bothered by the whole molecule. Just focus on the 6,5,4 carbon. Bottom one, the one below it, and the one right above that, and the one right above that. Those are the 3. And do with those 3 what I have done with the glyceraldehyde. Don't worry about that. Just worry about the bottom 3 carbons. Get them vertically, pointing away from you. So what is this? If that OH is on the left, what is this? L. This is L glucose. You guys have L glucose. I want you to make it D. How are you going to make it D? Swap it around. Swap that OH over to there and that hydrogen over to there. Get this OH on the right. I've come by. You show me when you think you have D glucose. We're not going to worry about all the rest of them above there. So make yours D. Where's your molecule? Okay, go make sure. Well, actually, this one is not. This one is not. Those are all chiral. No, it does matter. I want you to be bottom 3. I want you to get that one to be like right. Yeah. So this is carbon 4. So look right. This carbon is chiral. It has this. That's one. It has an OH. It's not a hydrogen. Right. That's 2. It has a CH2OH. That's 3. And it has this big clunky thing up here. Those are all different. In other words, I don't say that this is 1. I'm saying this whole thing right here. 1, 2. Yeah, so if I go up here. Well, the only one I'm going to have you worry about is this one right above here, because there is a carbon just like that on this route. We could walk on up here and say, okay, what about this one? What about that one? What about that one? Okay. Right. So half the time, you already have a. How you doing? What I do is I already have one. I'm looking at these 3 right here. And this is on the right. 1, 2.
So I was the part. So what I'm not usually.
We'll see in a minute if we're correct.
Well, I'm going to tell you like that. It is comparable to this one.
Just remember.
I want you to make
Because
that
the last 2
like
are the same.
Because if we start changing things around.
This one and this one don't count. It's just the middle.
Yes, this is.
Because it's always going to be C2OH.
This carbon is just like this carbon.
And depending on how
This
high
carbon, this is alpha relevant. This is alpha.
I love talking about it because you get that on it.
Right.
It makes everything.
Just like
Because the only thing is,
I like it. Well, they have everything. They have egg and bacon.
the song you do is
Yeah, see, see now, this is like this.
yeah,
This carbon is one. This carbon is like this carbon.
Her and her bad vibes. Oh, yeah. She remember carbon.
Yeah, the second from the bottom. Now, this is also chiral carbon, so the question comes up, where is it? And this is a chiral carbon, where is it? And this is another chiral carbon, where is it? And we don't have
Get
to
a
come up
little
with
traffic like
those
right
relevant.
around the rim.
But we could talk about each one of these. Now, you'll see a slide in a minute.
No, because I don't
that
get
shows you
until.
where they all will be. Okay. Everybody have D? Let me just look real quickly, make sure you have D. Yeah, you got D. Let me see yours. D, yeah. Let me see So I'm getting this up here. This down here. Good. Okay.
Probably with the boyfriend.
All right. So now, what's a Fisher projection? So I've got D-glyceraldehyde here. Which one? I've got D here and L here. So what we do with what a Fisher projection is, Fisher said, how can I draw this on a piece of paper, on something that's two-dimensional? How can I draw this three-dimensional molecule with a two-dimensional drawing so that I could, send an email to my friend or write a paper or whatever and then know what I'm talking about? So what Fisher proposed, and this is like about 100 years ago or more, he said, get it oriented just like we are doing, and imagine that you flattened it out in two dimensions. So you get it positioned just like this. Carbons going up and down. Here's my chiral carbon. So I don't even have to put a carbon right there. But there's my chiral carbon, and I got an OH over here and an H right here, and this is D-glyceraldehyde. All right? And if I were to take this one and do that, just to show you that the Fisher projection can illustrate the difference between these two, I might as well do it right next to that other molecule. Asenath, you better give me this after class. Okay, before. All right, so if I take the L-glyceraldehyde, same thing, carbons vertically, the carbonyl at the top. I know I can get in the way of you seeing this. And if I flatten that out on the board, I would have this up here. I would have my CH2OH at the bottom. And what would I have? I would have an OH over here and an H right here. Okay? This is the Fisher projection of this three-dimensional molecule into a two-dimensional drawing. It's the open chain of the monosaccharide. It hasn't been cyclized around. It's open it's going these three carbons. Well, this one can't cyclize around. It's only 3 carbons long. But it's the open chain. Carbonyl is always towards the top. If it's an aldose, it's going to be at the top. And if it's a ketose, it's going to be, you're going to see something like this for fructose. You would see this. You're going to have a carbonyl right there. And then you're going to have 1, 2, 3 chiral carbons. And then you're going to have another one of these at the bottom. This is not chiral, it's got 2 hydrogens. That's not chiral, 2 hydrogens. This only has 3 things on it, 1, 2, 3, not chiral. But the middle 3, these 3 carbons here on fructose. Fructose. How do you spell fructose?
You're right.
T-O-S-E.
Oh, okay. I thought there was another R there. Fructose. This is a ketose. And I'm just giving you that example to show you that even with a ketose, you put the carbonyl towards the top. It's not right on the top. But you orient the molecule. This is carbon number 1. This is carbon number 2, 3, 4, 5, and then finally carbon number 6. Okay, everybody with me? Okay, so Now, this is our real important reference point, because naturally occurring monosaccharides are D. They are the D isomer. D-glucose, D-fructose, D-galactose, D-ribose. Okay? They're all D. So nature makes these monosaccharides with the OH on the right, on this carbon. Okay, so now let's just go back for a second and look at that slide I had here a minute ago. I think it's number 8. Yeah. Okay, now this is a Fisher projection of D-glucose. So here's what you're going to have to remember, because one of the questions on the exam might be, one of the questions on your homework assignment is, draw the Fisher projection of D-glucose. And what is that? You're going to have right, right, left, right. Okay? That is D-glucose.
Because most of them are on the right.
Not most of them, all of them.
But the OH.
Yeah, most of them are on the right, but in this order. So from the bottom, it's right, right, left, right. You know, it's not right, left, right, right. That's another monosaccharide. It's a different monosaccharide. I'll show you all of them. I'm going to show you all of the aldohexoses and all these different positions that OH can be in, and what their names are. So fear is gripping you right now. Do I have to memorize all of them?
That's what I was thinking now.
Okay, pay attention. You'll know the answer to that in about 10 minutes. Yes, Minnie?
Quick question. Why is the OH changing, but then at the very top is staying the same? If it's number,
Well, Minnie, look at this. Look at this. It doesn't matter how I draw that. This can rotate around, okay? It doesn't matter what position this is in. I cannot get this over here by rotating it.
Okay.
I can rotate it like that. It got over there, but what happened to the carbonyl? It's on the bottom.
Okay.
Follow me?
Got it.
Okay, I could draw this. It doesn't matter how I draw that. All right, because there's free rotation around here. That doesn't make it a different isomer. Okay? So I could draw it like this.
Draw it upside down.
You know, I could draw them like that. It doesn't matter. This thing can rotate around. That's not changing the molecule. But I cannot get this over there and keep this up there without breaking this off and putting it over there. I can't do it with simple rotation. Okay? That's what makes this a fixed isomer of glyceraldehyde. There's no way by simple rotation that I could fix that problem. It's stuck there. Okay, good. That's a good question. Good question. All right. So let's go on here a little bit. So Fisher projections. Lines crossing through a chiral carbon represent bonds. The carbonyl group is placed at or near the top. Two molecules facing you or out of the plane of the paper are drawn horizontally. So that's the OH and the H. All right, so we're seeing these Fisher projections. So here's a 4-carbon one, erythrose. And I'll have a slide that shows a lot of these aldoses in just a moment, and which ones I want you to memorize. So there's D-erythrose, right, right. D-glucose, right, right, left, right. I'm going to concentrate on the D's now, because that is the naturally occurring ones.
So when you said are like produced by
Yeah, it produces D-glucose.
And we produce synthetically in the lab, we would produce
If we went and made glucose in the lab, which we could, we would make probably a 50-50 mixture of the two isomers. Because the wet chemistry we would do in the lab, just like you making the molecules, if we had 50 teams of students making these molecules, and I said, well, let me see what you made, probability would be 25 of them would make D and 25 of them would make L. They're just randomly putting it together. That's what's happening in the lab. The molecules are randomly synthesizing into glucose. But they're not randomly synthesizing out in the trees. The trees are piecing it together exactly the way it wants to, using proteins, and so nature can do that. Nature can do that. It can be highly specific about how it puts something together. This is a subtle difference chemically. This is a very subtle difference in molecules. They're going to react the same. The only thing they really do is rotate. I'm sorry, I don't know the order of my slides. The only thing they do differently is the way they rotate polarized light. We can take D-glucose and say, that's pure D-glucose. It will rotate polarized light in a certain direction, and L-glucose will rotate it in the opposite direction.
Clockwise?
I'm not sure, to tell you the honest truth. I don't know which one rotates it which way, but one will rotate it one direction, the other. And so what is polarized light? You just take a light bulb, you put it through a polarized filter, and what it's doing here, normal light is just oscillating, vibrating in all different kinds of directions. Polarized light is monochromatic. It's oscillating, just coming along here in a very nice distinct wave. Here's your sample. You would have a glass tube with your sample in it. That polarized light comes through there, and it has rotated that monochromatic light to a little different direction. Same wavelength, but it's been moved over to a little different angle. A mixture of 50-50 of the two isn't going to rotate it. Some of it is going to rotate that way, some that way, and it's going to end up pretty much the same. So chemically, it's reacting the same way. There are a few exceptions. You can find some L-lactic acid sometimes. The D-glucose is sweet. L-glucose isn't sweet. You can't taste L-glucose. Your body won't metabolize it. All right? When we get over to the amino acids, we're going to find that they are L amino acids. L-lysine, L-glycine. Well, no, glycine doesn't have an isomer, but all the other amino acids do, and they're the L form. And we're going to use this molecule, glyceraldehyde, as our reference molecule to decide amino acids. Okay, so there's D-glucose again. Another drawing of D-glucose. Right, right, left, right. Monosaccharides. Here's the example of fructose. Now you can see here, this would still be considered a Fischer projection. You don't have to ignore that carbon for it to be a Fischer projection. You can put the carbon in there or not. It doesn't matter. What does matter is that you get these OHs in the right order. Okay? That's what really matters. Right, right, left, right. How many times have I said that now? Okay? So let's start looking. Here is, and I'm going to put an asterisk on here. Here's where you can figure out which ones I want you to memorize the structure of. All right, we've used that as our reference molecule, D-glyceraldehyde. The only ones you have to memorize are D. They're going to be all D. In the aldotrioses, the only two that exist are D-glyceraldehyde and L-glyceraldehyde. So we're just looking at D. So there's only one D-aldotriose, and it's D-glyceraldehyde. Now, if you get up to 4 carbons, you have 2 chiral carbons. So there are 2 D-aldotetroses, D-erythrose and D-threose. I don't know why that's not D-phorose, but it's D-threose. That's a joke. Okay, I just thought of it. Okay, now this isn't a joke. You don't need to memorize either one of those. Okay? All right. You do have to memorize that one. D-ribose. And what is it? Right. It's got 5 carbons. It's an aldopentose. It's D-ribose. Why would I want you to memorize D-ribose?
DNA.
Okay, you're real close. RNA. Good. You were right on the money. This is the what does RNA stand for? Ribonucleic acids. When we get to chapter 20, you're going to see that there's a sugar phosphate backbone, and the sugar phosphate backbone of RNA is built off of ribose. D-ribose. Right. So that's the only one. But here's 3 others that have 5 carbons. Right, left, left, left. You see how these chiral carbons are giving rise to families of molecules. All right, now here are the aldohexoses, and here is our. Probably didn't even need to ask about that one. Yes, you need to know how to draw D-glucose. Right, left, right. And I also want you to know how to draw D-galactose. Galactose. This is the monosaccharide in milk. Glucose and galactose are in milk. So lactose is made up of these 2 monosaccharides. And so glucose is right, left, right. What is galactose? Right, left, right. These are Fisher projections of these molecules. And then the only other one is fructose. It's not on here, because these are all aldoses. Okay, so there's 5 monosaccharides that you should make 3x5 cards of and know how to draw them. So galactose, just to use that as an example, I mean, one, two, three, 4. You can draw just like that. And galactose, you're going to need it right, left, right. You don't even need to put the hydrogens in.
That's galactose?
Yeah. Is that galactose?
Yeah.
So this is D galactose. And why is it D? Because that is identical to what you would see on that carbon on glyceraldehyde. It's on the right.
Is that another one we need to know for sure?
Yeah, it'll come up in a slide, and we'll toss the OHs on there. Okay. I guess we had fructose a minute ago. Okay. All right, so glucose is the most important sugar in the human body. Fructose is sweeter, about 73% sweeter. So when you eat grapes and you say, wow, grapes, they've got a lot of sugar in there, maybe the sugar they have in there is fructose, and it seems sweeter. Gram for gram, the fructose actually seems sweeter than glucose. They're solids at room temperature. Go home and look at your sugar bowl or a bag of sugar. You evaporate off all the water, and what do you have? You got white crystal solids that are very soluble in water. Why? Because of all the OHs, and it allows it to be transported easily. Okay, now let's move on now. Here is a word that's popping up here that popped up in chapter 13 when we talked about aldehydes and ketones. Remember, I had you learn the hemiacetal. Let me look at this again. Let's just review that real quickly. The hemiacetal reaction was this. Let's say you took methanol and reacted it with let's react it with acetaldehyde. What's the hemiacetal reaction? It's the addition of an OH across a carbon-oxygen double bond. And where does that go? The O goes onto this carbon, the H goes onto that oxygen, and this bond disappears. So let's actually draw the product. So I'm going to repeat. No, don't need that bond. I'm repeating that over there. That's what happens. You're adding across a double bond. When you do that, you eliminate one of the two bonds in the double bond. The H goes on the oxygen here, you get an OH. The rest of the alcohol, the whole rest of the alcohol attaches to this carbon right here. And you get that. This is a hemiacetal. It's the hemiacetal reaction. It's a reaction of one alcohol across one carbonyl. Well, okay, any questions about that? Let's review. But it's a fairly complicated reaction. And so if you're reminding yourself what that's all about, I understand. Okay, you got that?
So that's not like an ester or anything like that?
No, that's not an ester.
When there's the oxygen between two carbons, that's just what it reminds me of.
Right. It does remind you of an ester, but an ester would be this. The double bond is still there.
Oh, okay.
Okay? The ester, that double bond hasn't disappeared.
Okay.
But in a hemiacetal, it has. You've converted the double bond into an OH and a single bond.
What did you say the hemiacetal was again?
It's the reaction of one alcohol, OH, with a carbonyl, carbon-oxygen double bond. So that's the hemiacetal. Reaction of a carbonyl.
So it's kind of like an ester, but that double
With
bond is broken.
a COH. Yeah, I wouldn't call it an ester. And I don't get used to, I wouldn't make that comparison. It's not an ester.
I'm just saying it kind of sort of is like it, minus a double bond.
Yeah, but we got an ether and an alcohol, is which results. Okay, now let's switch over to glucose for a minute. What do we got here? We've got a carbonyl right at the top of the molecule. And what do we have here? We got OH groups. Okay? So we have all the ingredients that are needed to form a hemiacetal. Now let me tell you what happens. This molecule doesn't just randomly. So this, well, could it react with that OH? It really can't. It's too far away for this OH to be the OH that reacts with that carbonyl. It's too far away. Could this one do it? Well, maybe. I could wiggle this around and we're getting close. I could certainly wiggle this one around and say, well, yeah, that really has some potential for that to react with that. But what glucose does do, this is carbon number 1, 2, 3, 4, 5. See carbon number 5? It has an OH on it. So let me do a little, let's wiggle this molecule around a little bit. And that OH can come up right next to that carbonyl and form a hemiacetal. And what's going to happen, the glucose is going to cyclize. It's going to end up in a circle. Now watch me. All right? So what I said is this bond breaks, this double bond breaks. Put that in there. Okay. That double bond breaks, and the hydrogen, come here with me. Exhibit A, turn around, hold that. No, you first face the class. Okay. There you go. Hold that. Hold that carbon right there. Put your hand down. Hold that carbon right there. Okay. All right, so we broke the double bond. The double bond was right there. Breaking the double bond, the hydrogen goes onto that bond. And this oxygen bonds to that carbon. You with me? All right, thanks, Whitney. And what do you end up with? You end up with an OH, where you had a carbon-oxygen double bond. You end up with an OH. And where you had an OH, you end up with a carbon-oxygen-carbon bond. And you end up with a 1, 2, 3, 4, 5, 6-membered ring. All right? And it's not in a chain form now, it's in the cyclical or ring form of the D-glucose. Everybody with me? All right, now try to go ahead and do that. React the OH of carbon number 5 with the carbonyl that's at the top of your glucose and see if you can come out with something that looks like this.
Is that
Yeah, you use the chiral carbon. No, don't use the 6th one. Do the 5th one. 5th one. Leave that 6th one out there.
It's crazy. It's like this.
Well, the first Proj, I was 6, so the second one I was 1. Did you take this double bond?
So one, I woke up the right compartment, so I was just like, when she took it, I woke up connect the red one to the first one.
This one? Yeah, you have to take, no,
We're not charged. I've been trying.
And then where's the,
I'll scare her.
on the red one by itself. Yeah.
So if I die,
You just hear
Okay. Okay, Gabriel, we never got back to the OHs on there. All right, now this gives rise. Now you are in the territory of, okay, how do I draw this molecule? And Haworth is the one that attacked this problem. How do we draw the ring structure in such a way so that we kind of know what we're talking about? Well, here's this would be D-glucose again, and I'm going to show you how to draw these in just a second. And I want you to have a little blank sheet of paper. But there it is, cyclized. This is carbon 1, 2, 3, 4, 5, 6. This is carbon number 6. You kind of know that because that's where the molecule ends. It ends at a CH2OH, whether it be glyceraldehyde or glucose. It ends at a CH2OH, and that is the end. The carbonyl, this carbonyl is that oxygen right there. It's become an OH. 1, 2, 3, 4, 5, 6. Now, when this thing cyclizes, some of you probably have alpha D glucose. This up here is alpha D glucose. And this is beta D glucose. So when you start seeing the alpha and beta prefix on these things, you're talking about a cyclized form of the monosaccharide. When we just talked about D-glucose, we were just talking about it in the open chain form, D-glucose. But now we're in the closed ring form of it, and you could end up with this OH above the ring, it's beta D-glucose, or below the ring is alpha D-glucose. So what do I mean by that? Let me show you how to draw it. So the way that helps me is to think about this as a trampoline in the back of the yard with a screen around it, okay? Probably doesn't help you yet until you see my drawing. So if you were to draw a 6-membered ring with the oxygen up in that corner, okay? That's how you're starting, right there. An oxygen up in that corner. And then there's your trampoline. And then put legs on your trampoline. All right, so that's starting to look like a trampoline? And your CH2OH is going to be above the bed of the trampoline. And then for D-glucose, you're going to have, this is carbon number 1, this is 2, 3, 4, 5, and this is carbon number 6. That's a 1 down in there. So you're going to have an OH down below the bed of the trampoline, an OH above it, an OH below it, and a CH2OH above it. Okay, now, if the OH is here above the trampoline, it's beta D-glucose.
Beta is the one found in nature?
They're both found in nature. Alpha and beta both exist.
If it's where? What did you say?
If it's above the bed of the trampoline, it's beta. And so alpha would be
Do you know why that's beta? I mean, I would think it was alpha because it's
above.
first.
I don't know why. If they had, it was probably developed in a non-English environment. Because, I mean, it would be nice for alpha to be above, A above, and beta to be below, but it's the opposite of that. Beta is above, and alpha is below. And I think your homework, I don't know if your homework asks you to draw both of these, both of them?
I think they're both D.
Yeah, they're both D-glucose. One's alpha and one's beta.
So you're going to do beta D-glucose and then beta D-galactose.
Yeah, okay. So beta, the OH is going to be above on both of those. Beta D-glucose and beta D-galactose is going to have the OH above there. This is glucose. What's going to differ is where this OH is for galactose. Okay, so this is a Haworth projection. So this is the Haworth projection. So when you hear that term, you know you're talking about the cyclized form and drawing of it. How do I draw this cyclized form? So you could, for example, Kelsey, let me see yours again. You guys just randomly made this thing, so you can take this. So here I got this molecule, and what am I going to do? I'm going to make it like a trampoline. So the 6-membered ring, I'm going to make it horizontal. And I got the CH2OH group up here. And where is the OH? Top. So this is what? Beta. All right? I didn't instruct you to do it any particular way. Just do it, and randomly, depending upon where this was spinning or where this was rotating, it comes out above. Does anybody look at yours? Did yours come out below? Did you guys? Oh. Anybody have one that came out below? No, you didn't do it right. You know why you didn't do it right? There's no oxygen in your ring. See that? You got to have an oxygen in your ring. Well, here's what you got to do. You've got to get this above. Right? I mean, yes, that's above, but the CH2OH is below. Get that above and then ask where is it. So that is alpha. Yours is alpha. You don't have to change it. They both naturally occur. They both occur. It just happened to be which way of the way you had that rotated. Alpha and beta are both correct. The thing is just which one did you make? You made the alpha.
Serious? No, it's not like your sister.
Okay, so you're looking at it this way. Oxygen behind you, and you've got this up top. This is towards the back of the trampoline. Above. So that's
You're like, I've never heard that.
If you wanted alpha, you would switch around. But these both naturally occur. Alpha and beta.
Are we looking at the carbon after the oxygen, carbon, oxygen, carbon?
Like,
This one?
Yeah, that's.
Yeah, that's carbon number 1.
so on all of them, we're deciding whether it's alpha or beta, we're looking at carbon 1 and 2.
Yeah, this is carbon 1.
Any molecular.
Yeah, I got you. Yeah. All right. Did you fix it? Did you fix it? Okay, now get that like I don't know what you did, but
It's not right still?
no, it's still not right.
What?
Because this should have an OH on it, and that thing should be over there. I don't know what you did. If you get it back to D-glucose, I'll show you how to get it there. I think that's right. Yeah, so there's your CH2OH up there, and that's above, so that's beta. Okay. Okay, let me just say it again to the whole class. Alpha and beta exist. You'll see disaccharides that, well, there's one disaccharide that is one alpha D-glucose and one beta D-glucose is a certain, is one of the disaccharides. This is just another depiction of it. There's your D-glucose in the Fisher projection. You can see if this thing can rotate around, as I was answering Minnie's question a minute ago. This molecule can rotate around, not molecule, this carbon, this bond, it can rotate on that bond. So depending upon where it is oriented, when the OH adds across that double bond, you can get it above or below the ring. And there you get the alpha D-glucose, beta D-glucose. And so here's the alpha D-glucose. I'm ignoring the hydrogens. Below, below, above, below is alpha. Beta, above, below, above, below. Just alternating through there, and you got the beta D-glucose.
So beta happens more than alpha?
Apparently. The body will make the one it wants, okay? Because when it makes this disaccharide that has one of each, alpha and beta, it's not doing that randomly. It's orienting them the way it wants them oriented to make that disaccharide. I think what this is suggesting here is just naturally, I mean, if you just chemically went ahead and cyclized D-glucose, yeah, you would get a little bit more beta than alpha. Let me see if I could say why that might be. Probably just because of this proximity and just what we would call steric hindrance. Too much, not enough space. There's more space for that OH up there. So naturally it would go up there, eat more easily. That's just another one. This is fructose. Don't worry about drawing fructose too much. I'll just point it out. Fructose is going to make a 1, 2, 3, 4, 5 membered ring. There's going to be an oxygen in there. But see, here's your carbon 1, 2, 3, 4, 5, 6. So you have two CH2OHs and they don't get in the ring, so you end up with a 5-membered ring. That's a furanose, or a furanose ring, 5-membered ring. The glucose is a pyranose ring, pyranose. All right, here's the pyran ring, 1, 2, 3, 4, 5, 6. Furan ring with fructose, 1, 2, 3, 4, 5. Reducing sugars, I'm trying to get through. Let's see what slide we're on here. 35. Only 20 more to go. No. So I'm going to just gloss over some of these. Don't worry too much about this one. This slide is just the explanation for why fructose will give a positive Benedict's test when it is not an aldehyde functional sugar. Benedict's reagent, Benedict's reagent, it gives you a positive test with glucose. A number of you have seen that in the 1107 lab. You shake your head if you have. Remember that? Glucose, it turns from blue to like red with glucose. Well, we'll do that with fructose also. Even though fructose is not an aldehyde, it can rearrange into an aldehyde and give a positive glucose test. That's enough said about that. Phosphate esters. Here's beta-D-glucose 6-phosphate. So we're attaching a phosphate onto the 6th carbon there. The CH2 is becoming a phosphate ester. Glucosamine. This is a supplement some people take for joints, bad knees or whatever. They'll take glucosamine. Helps with the joints. Glucosamine. What have we done? We've replaced this OH with an amino group. You're going to find this in the body, glucose popping up in many different places in different forms. All right, now we already talked about ribose. And remember, ribose is 5 carbons long. 5 carbons long. And where are the OHs? Right. All of them. All of them are on the right. Now this is deoxyribose. Now someone mentioned DNA. This is the sugar that is in DNA. This is the sugar that's in RNA. Ribonucleic acids. D. This D does not stand for that D. This D stands for this D. Deoxyribose. What does that mean? We've taken that oxygen out of there. That is a very unique monosaccharide that ends up in the backbone of DNA. It's about the only time you're going to see a monosaccharide with not an OH on about every carbon. Deoxyribose. Okay, you don't have to memorize that structure, but just know what that means. We have removed an oxygen from here, and that is the sugar phosphate backbone for DNA. So DNA has not a very different, but a subtly different sugar phosphate backbone from RNA. Now DNA is in the cell nucleus, all right? RNA goes in and out of that cell nucleus, but the DNA doesn't. The DNA is in the nucleus of the cell. That's the mothership right there. That's the molecule that's dictating everything that's happening, and it is protected in the nucleus, and RNA is the messenger molecule that's coming in and out, or DNA is actually making to send out to make proteins. We'll see more about that later. Fructose, I'm not going to dwell on it. Okay, Gabriel, this answers this question. Right, left. Okay? And that's fructose. Right, left. Fructose. And know that it is a ketohexose. 6 carbons long. but it has the carbonyl on carbon number 2. All right, galactose. Here is beta-D glucose. Here is beta-D galactose. What do we got here? Bottom, top, bottom. Beta-D galactose. Bottom, top, top. Above, below, whatever you want to call it. There's also beta-D galactosamine. All right, I'm not going to finish yet, but let me go to the last couple slides, and we'll do disaccharides and polysaccharides real quickly on Wednesday, and then get into chapter 17. But I just wanted to show you where else these monosaccharides show up. Blood antigens. So type AB, and O blood types. What is dictating that blood type? What's governing that? These little tetrasaccharides, 1, 2, 3, 4. Some cases there's 1, 2, 3, 4, 5. These rings now are representing monosaccharides. So let's see if there's the galactose. Is that what that is? Galactose. This is galactose and some other monosaccharides, but arranged in a certain way is dictating what blood type you have. It's these things attached to the side of the hemoglobin that is governing that. All right, on Wednesday we'll do chapter 17. We'll get started into it. If any of you have printed off chapter 17 slides, has anybody done that already? You may want to do it again. I just modified it. And made it about 6 of the slides a little better to read than what we had there. Substantially, the information is the same, but there were some where the reactions were real tiny and hard to read, and I made them bigger.
What time did you do that? I just printed them off before class.
I did it after 10 o'clock.
I'll check. I'll compare.
Yeah, and so then I took it off of Canvas and I posted the modified ones back up there.
Are we done with these, or do we need a roll?
I'd like them to be torn up. Do you want to do it next? Do you want to do it on Wednesday?
Yeah.
We'll tear them apart on Wednesday? Okay, then put them on the back shelf, the bottom shelf. Do not put them on the top shelf, because the next class needs them. So put